the previous lecture, we did a quick overview of qubit technology and the current status. We also looked into various candidates for realizing quantum information technology and qubits. In this lecture, we will look into the qubit realization or the fundamentals of qubit realization using superconducting circuits. We will overview the quantum mechanics of an LC oscillator, and then we will move on to superconducting qubits and how the superconducting qubits will act like a LC oscillator. Okay. Just like what we discussed in the previous lecture, the current qubit technology revolves around atom or atomic physics. There are two kinds of atoms that we deal with in this context. One is a natural atom, another one artificial atom. So the qubit candidates or the systems or quantum mechanical systems which are used to realize qubits fall into broadly two categories. The first two here are based on natural atoms with a roughly shown potential roughly shown here. The first two picture here shows how you trap atoms using laser fields in optical lattice and use the atomic states to store and manipulate the information using its quantum state. The second two, this also we have discussed using the ions, which trap using electric and magnetic fields. And there are a couple of different configuration. The recent development is micro ion traps, where the whole thing you can be realized on a chip. And the last two, this one represents superconducting qubit, and this two represent semiconducting qubits or spin qubits. So superconducting qubit has a rough parabolic shape confinement, and semiconducting qubit, that confinement potential depends on the details of the gate designs and stuff, but they could be parabolic or square well kind or a mix of these, but those are details which we leave to the design context. So but in any case, we are always dealing with atoms, either they are natural atoms or artificial atoms. Here this table summarizes the main parameters or main points of all these different systems. So for the natural atoms or ions, we have to use optical frequencies or electromagnetic waves in the optical range to manipulate the states. Whereas for the superconducting and semiconducting, this is like a few gigahertz to 10 gigahertz range. That means this is the optical regime, and these two are the microwave regime. And the dimensions for these ultra cold atoms or natural atoms, those are the ones shown here. And ions are also, they are pretty small. I mean, these are like atomic dimensions, whereas the superconducting circuits are much larger, and semiconducting circuits are also large but smaller than the superconducting circuits. Okay, and the interqubit distances are much large, or you can get really large for the trapped ions, whereas for the superconducting and ionic trapped ion based ones, these are micrometers. Okay, whereas for the optical lattice and also for the spin based one, those are like hundreds of nanometer to tens of nanometers or hundreds of nanometer. And the next operating parameter is the operating temperature. So here these are in the microkelvin, nanokelvin range, but those are not really the physical temperature of the system. Those are the energy of the system. Okay. Whereas these experiments are conducted at cryogenic temperatures, millikelvin to, Kelvin, sub-Kelvin, few millikelvin range. Okay, and of course, some of the spin qubits you can even do operations at room temperature, but those are not really the quantum dot based spin qubits as we have shown here. Those are like implanted ion kind of spin qubits, which are not really scalable systems. So we don't really consider that as a scalable system in this, and that as a series candidate at this point. Okay. Now, how the cooling, how do you get the system to operating the regime? Those details are here. And as I told, these are laser cooling and trapping technology, whereas this relies on cryogenic technology. And how you manipulate the states here, you need to use optical and microwave cavities, whereas here we are using transmission line kind of LC circuits or microwave cavities. And here also transmission line LC circuit microwave cavities, and optical for the implanted ion kind of qubits. That is the quick overview of the current leading candidates for qubit realization. Now, what we just summarized is we need some kind of confined systems, and we use the states of the confined system as qubit states. Now, one of the most common confined system with well-defined states and easy to understand is a harmonic oscillator. This is an illustration of a harmonic oscillator where a block with a mass m is tied to a point using a spring, the spring constant k. And this is a standard textbook problem where I'm sure almost all of you guys have actually gone through. And this is the Hamiltonian, where this term is the kinetic energy term and this term is the potential energy term. P square by 2m, kx square by 2. And in the x versus energy space, that's going to give you a parabolic confinement. And you have these equally spaced energy levels with n is equal to 0, 1, 2, 3, which is also something which is known to all of you. But that is the case with the mechanical oscillator. Okay. But the devices need to be electrical, and an electrical analog of this quantum harmonic oscillator is an LC circuit. We have a capacitor and an inductor in parallel, and these two can set up an LC oscillation where the energy stored will oscillate between the capacitor and the inductor. And that is the direction that we are going to lead our discussion, qubit discussion. This is the Hamiltonian for the LC oscillator, where half CV square is the energy stored in the capacitor, half Li square is the energy stored in the inductor. Okay, so that the energy is partitioned between these two. Okay, now just by a simple substitution, Q is CV and phi is L into I, where L is the inductance and C is the capacitance. You can rewrite this Hamiltonian as H is Q square by 2C and phi square by 2L, where phi is the flux due to the current passing through this inductor. Okay. Now by using some substitution here, like I'm going to substitute n is q by 2e, where q is this charge and 2e is the charge of a copper pair. Now remember, our discussion we are leading into the superconducting qubit. So I'm going to assume the charge here is the charge of copper pair, that twice the electronic charge. Okay, that q by 2e. These are just parameters which we are going to substitute to get this Hamiltonian in a very simpler form. And phi is 2 pi phi by phi 0. This is the small phi here is the basically the phase term. Phi is the total flux and phi 0 is the quantized flux or flux quantum. That is h by 2. And the charging energy is E square by 2c because C is a capacitor, and we are assuming that these are microscopic systems, so the charging energy can be significant. It's not a small quantity. That also you need to consider. And EL is the energy in the inductor, that is phi 0 by 2 pi square by L. Once you substitute all these things, you can rewrite this Hamiltonian as h into 4 EC n square plus 1 by 2 EL into phi square. Again, you got a parabolic relation for the potential, that is in terms of phase and the energy. You can get this also parabolic in N2. Okay, this is parabolic here also, but there is a small detail there which we will get into in a minute. The difference is n is a number that is not a continuously varying quantity. That's a discrete number. Okay, but we will soon change that to a continuous quantity in a minute. Okay, just wait for that. But for the time being, let us focus our discussion onto phi versus energy, and that is a parabola. And these are energy states 0, 1, 2, 3. Now the assumption or the idea is we want to encode these zeros and ones or the qubit states into the lowest two levels, the ground state and the first exception, 0 and 1. But how do you actually manipulate these states? You use radiations with h bar omega, which is equal to this energy spacing. Okay, but now for a simple parabola like an LC oscillator, which corresponding to an LC oscillator, that is discussed here. Okay, this spacing between all the energy levels are equal. They are all h bar omega. Okay, that is the characteristics of a parabolic confined system. So when I try to basically manipulate these two states, they can have transition between all other states also. So you don't have much control on which two levels you are actually using for this information processing. So selecting only the lowest two states is not really possible in this configuration. That is a real issue, which is not the case with atomic systems or the square well systems, because spacing varies. Whether you have a Coulomb potential or confinement provided by the Coulomb potential or the square well potential, the spacings are not equal. So you can select any two levels there, and it's easy for the qubit because you can select the bottom two levels and you can fix your transition or the frequency that you are going to apply to make this transition equal to the difference between those two energy levels. But that is not really the case here. So now the question is, how do we select the bottom two levels? How do we modify this potential? And that is a very interesting situation. So let us look at a Josephson junction for this purpose. That is exactly where the Josephson junction comes very handy. Josephson junction, which we have learned in great detail in one of the previous modules. What you have is two superconducting electrodes, and there is a junction. These two are superconducting electrode, and there is a thin insulating layer like a nanometer or so in thickness. Okay, that is a Josephson junction. Okay. Now, what I am going to do is I am going to take this Josephson junction and replace the inductor with that. The capacitor is still there, but Josephson junction is our inductance. Now, from the Josephson equations, we have the current through the junction is IC, that's a critical current, into sine phi. Phi is a phase difference. And the voltage to phase relation is the time derivative of the phase is proportional to the voltage. Okay, QV by H bar. And where phi is the phase difference between these two sides. Now, this V you can rewrite as H bar by 2 E into d phi by dt. Now, 2E by H is H by 2E is your flux quantum. Okay, phi 0 by 2 phi into d phi by d. You can rewrite this. Now, what we have, our variables are current and voltages. So what we are going to do is we will replace this d phi by dt with the di by dt. What you do is you take this and differentiate it. You get this relation. Okay. Now you substitute that here, d phi by dt from here. So you will get this relation. And voltage is some inductance into the time rate of change. Okay. So that inductance LJ stands for the Josephson junction inductance here is phi 0 divided by 2 pi IC into cos phi. Now you have run into a very interesting situation here. And using the Josephson energy EJIC by phi 0 divided by 2 pi, you can rewrite this Hamiltonian in the previous slide in this form. Now, whether from this equation or from this equation, you actually ran into a very interesting situation. That is, previously you had a Hamiltonian which is parabolic in phase, because there is a phi square term, or parabolic in flux because there is a capital flux square term, okay, capital phi square term. Now, but that L has now, because L is the frequency, L square root of 1 by 2 pi into square root of LC is the frequency of this oscillator. That frequency decides what is the transition frequency, h bar omega. Now, since L is now a function of phi, is a cosine function of a sinusoidal function of phi. Now you can see that as we increase the phi, this frequency will decrease. That means the levels will get closer and closer and closer. So originally you had a normal LC, you had a parabolic confinement given by this red. Now what you have is a sinusoidal confinement for a Josephson junction given by this blue curve. And that's what this also says. Okay. Now the energy is an oscillating term, sinusoidally oscillating term in phase. Now it's very easy because now the spacings are different with different levels, between different levels, because the frequency is a function of the flux, the phase term or flux. Okay. So now by introducing the Josephson junction as the inductance in the LC, what you have done is you have reshaped the normal LC similar harmonic oscillator potential into a sinusoidal one. Now this will make sure that the transition frequency between different levels are different. That is, h bar omega 01 is different from omega 12, different from omega 23, like that, and so on. So this will enable you to basically get a robust subset of states as qubit states. And that is the idea, or that is the basically the underlying idea of using Josephson junction circuits as qubit states. Now, let's look at what are the different realizations. This is the Hamiltonian, or this is the potential which we got from this Hamiltonian. Now what you have here is 4 times EC n square. N is the number of the Cooper pair running into, and phi is a flux difference between the two sides of the junction. That is what you have. And you have two kinds of, basically you have two kinds of states here. Either they are charge state, the information is encoded in the charge state. Okay, that is charge state, basically a Cooper pair box. That means you have two Josephson. We have two junctions here. Okay, each basically it's a box. It's a just a single electron box. Here it's a superconducting box. A box, a small island made of a superconductor, and you basically look at the charge state of that. So for the charge state to be robust, what you need is the coupling to the circuit should be minimal or small. That means EJ is a measure of the coupling. So EJ by EC, that should be very small. That means the charging energy should dominate. That is when you get a charge qubit. Other than the opposite extreme, in other extreme, you have phase to be robust, you have charging energy is small compared to the Josephson coupling. That's the other side. Now let's look at this practical situations. You can, of a charge qubit, which is one of the first qubit system, realized in Josephson junction circuits using Josephson junction circuits. The Hamiltonian is 4 EC n square minus EJ into cos phi. But n is the charge of the Cooper pair. But remember, this also uses gates to control the charge state, potential, and there are also spurious effects, gating effects using impurities and other things, and fluctuation, electric field or voltage fluctuations. So that you basically call offset charge, and that also is going to contribute. So you have discrete charge, that is n, and you have a varying charge because of various other effects, electrostatic effects that you observe in Ng. The total charge is a sum of these two, n minus Ng. Okay, so you have to replace n by n minus Ng. Okay, so when you do that, this will be the final Hamiltonian. Now, what that means, the energy state, there's a square term here, the energy state is very, very sensitive to this offset charge. So a small disturbance, electrical disturbance or charge fluctuation or anything in the vicinity will act as a decoherent or decoherence source of basically decoherence. So because of this, the coherence time of these qubits is very, very short. Okay. So that this problem was now rectified by a very clever design. So this is our original Hamiltonian, this is our new Hamiltonian when you consider the offset charge. Now the idea here is, you go to a regime where this EJ by EC is something like 50. So let's look at what happens when you vary EJ by EC. So remember, I told you this is now, this Hamiltonian is now parabolic in Ng and sinusoidal in phi. That's what this Hamiltonian is now. Okay. So when I plot Ng versus the energy of these states, you get a set of parabola. For each parabola, the n is stable. When two parabolas meet, that is this point. I'm talking about only the red curve at this point. Okay, the n can vary. That is the only place you can. That is the charge degeneracy point. We have discussed this in great detail during the single electron transport, but you have to assume here it's not single electron; these are Cooper pairs. Okay, that's it. Okay. Now, that the mathematics remains same, absolutely same. Now what we have here is we have plotted this EJ by this energy for various values of EJ by EC. So what I'm saying is the spacing between these first two, n is equal to say 1 and 2, with these first two levels or second other two levels, doesn't matter. They're all very strongly depend upon the offset charge because it varies very fast. Any small charge fluctuation can change the spacing. The spacing is maximum here, is minimum here, but it's very easy to get a disturbance or very easy to change the state. Okay, but small fluctuation in the charge. But now, if you make the ratio EJ by EC in this Hamiltonian larger, you can see that these oscillations or these parabolas get smoother. And when it reaches around EJ by EC is 50, all this looks pretty like straight line, and the spacing is almost independent of the offset charge or charge fluctuations. And that is the proposal, or that is the current, state of art, where you use a shunting capacitor across the junction, parallel to the junction, so that your EC term will, without disturbing anything else, the EC term will come down, so that the EJ by EC term you can increase it, but it's not like really large where in the flux qubit regime. This is still in the charge qubit regime, but EJ by EC is something like few tens, okay? And that is the whole idea of transform qubit. It's actually a charge qubit, but it's insensitive to charge fluctuations or charge noise. So you have transform qubit has basically two Josephson junctions. These two represent Josephson junction, and there is a shunting capacitor here. And you can use the idea of two is because just by changing the phi here, you can tune the phase, okay? And the shunting capacitor will make sure that this EJ by EC term is larger. Usually these shunting capacitors are long capacitors, long, interdigitated capacitor, which is shown like here. So what we have is you have two Josephson junction. This is the magnified view of the Josephson junction, and this is the magnified view of one junction. So you have a junction here, okay? And this is in parallel. This capacitor, these two green area are two interdigitated plates that is going to give you the required capacitance, and you can tune it by tuning the number of the bends in this design, okay? And there are other circuit elements are there which we will not go in detail, but this is lecture is just to give you an overview of what is the current state of art. Okay, so this is one qubit, and IBM has basically demonstrated many qubit system recently, okay, and a practical quantum processor also. But here what you are seeing is just 2 qubit system, 3, 4 and 8 qubit systems, where you have the qubits in this, similar to this design. So that is the current state of art. Transform is the current state of art for the superconducting qubit technology. Okay. So just to summarize the superconducting qubits, here you can have flux, phase, state, charge and hybrid qubits. They are highly scalable. That means you can use microfabrication techniques to make many in a very structured manner with whatever the architecture, whatever you want to. And they have demonstrated all kinds of types of qubit. Coherence time is like 10 microseconds, tens of microseconds. It's not very long, but it is not bad. Okay. Universal quantum gates have demonstrated. And mainly it's very easy to fabricate because most of them are simple aluminum oxide, aluminum junction systems. Okay. And well, fabrication is well controlled, and the distance between the qubits is actually a micrometer, which is easy to fabricate. Okay, so many qubit systems have been demonstrated with a good fidelity, but operation range is in millikelvin again. Okay, and you can read out this qubit by using you can SET, you can, which reads SET single electron transistor, that also we have discussed in the previous module, in one of the previous modules, that you can read the charge state or the basically the flux or the phase by frequency shift. You can read out all these things. You can control this using microwave pulses, voltages, currents, and all these things, all electrical. Okay, there are no optical elements here. Everything is electrical. Everything is circuit. Okay, and these are some of the parameters. I mean, benchmark parameters for T1, the longitudinal transverse coherence times, and other gating times and everything. So, in summary, the superconducting qubit community has demonstrated pretty much whatever is required for the operation for realizing a prototype. They have realized also a prototype quantum computer. And in the next lecture, we will look into we'll overview the technology of semiconducting qubits.